students are posed with the essential question, how do I calculate the voltage, which they're reminded is energy per charge, generated by a ... generator? Okay. And we did a practice calculation, estimate the voltage of a thundercloud from which lightning strikes the ground 100 meters below, by considering that the electrical breakdown in air is 40,000 volts per centimeter. So this Van de Graaff generator, you can see it's got like some elastic belts here. On the bottom of it, there's like a piece of felt. So once we turn it on, this sort of elastic band, so there's a motor in here that's going to sort of take electrons from that and then deposit them on this metal sphere here. The electrons on the metal sphere are going to sort of spread out, right? They're going to repel each other. So we can sort of deposit a certain number of electrons on this. What's going to happen when we have a huge amount of charge in one place? Charges create, what are we studying? Electric fields, right? Electric fields. So like, I'm made of charges. I've got protons and electrons. And the atoms that make me up, but there's just as many, right? So most things are neutral. So we need like a clever way to get a bunch of charges in one place. You ever rub the balloon on your head? Maybe I should do that. Can't blow up a balloon. Should have anticipated that. In any case, if you've done a rubber balloon, you know that you're sort of forcing some charges, right? You get some static electricity. So that's the same idea here. We're going to deposit a tremendous amount of electrons here, and we should create an electric field sort of around this. So if your hair is standing up on end when you rub your hair with a balloon, why does that happen? Have you ever like turned on a TV, maybe one like that, and like the hair on your arm kind of stands up on it? Something like that. You feel kind of like there's an electric field there too. And that's because the electrons are sort of being deposited here. They conduct through, and as the electrons go on these things, what are they going to do? They're going to repel each other. All right. So let's see that. Even though it's powered down. Okay, let's do that. So we definitely saw evidence of that electric field, right? So the electrons are positive, they repel each other. Okay. Back to the essential question: how do I calculate the voltage generated by this generator? We're doing science, it's like a magic show. Like, oh, this is cool. You know, said yeah, these are like planetariums. It is cool. So Van de Graaff was like, try to rub this balloon on my hair. I'm gonna find a way to, you know, deposit some charges here. This is like, you know, the staple sort of mad scientist kind of apparatus, or a Jacob's ladder. The Van de Graaff generator. Okay, so let's have some ideas on this. How do we calculate the voltage here? How do we calculate things? What do we need? Yeah. You mean E for electric field? Oh, energy per charge. Okay, I see what you're saying. Use the energy per charge definition of voltage. So we have to measure the energy and measure the charge and then divide those two things. How would we do that? How can we measure like the energy? Maybe, you know, it's like, is it equal to like the energy of, you know, like the kinetic energy of this thing? Is that where the energy is coming from? Or like electrical energy is really kind of like the charges themselves. Like if we're stealing electrons away from this little belt here, we're putting them on here, right? So this elastic is sort of up past it, pulling electrons up, and then there's a little part to sort of take this lid off here. You can see that there's a little honeycomb kind of thing where the charges jump from that. You can sort of all of this and spread out. So you're absolutely right. In science, if we define something and we can measure those things like we did speed, we said, hey, measure distance, measure time, divide it. That's how we do it. So you're right. We can measure like the energy, we can measure the charges. We have to sort of like count how many there are. It's like, there's this many electrons, they each have elementary charge. Bingo, there's the charge, the energy. I really don't know. So you're right, but I think it's impossible. Or it's not impossible. It'd be very difficult, I think, to collect those measurements. you have to like measure something else. Like usually energy is like one of my favorite labs when we talk chemistry or even middle school science. What we have to do is like calorimetry. It's like how many calories are in a Dorito. Well, how are we going to find that out? Let's set it on fire. Right? So you burn a Dorito and you let all of its energy heat up some water, and we know sort of how much energy it takes to heat up water because of the specific heat is known. And then you can say, oh, well, this much energy went into the water. You assume sort of, no energy was lost. You calculate how much energy there was in that Dorito. You burned all sorts of different foods that way. So maybe something like that. You have to say, like, the energy doing something else that's easier to measure. If you look at the slides on word energy powers, like James Joule, the guy who named like the moon after, he had all sorts of experiments with like converting thermal energy into mechanical energy so we can measure it and kind of honor by moving the lunar event after. So that's a good idea because it's like, yeah, that's how we could do it. But let's think about the equations that we have at our disposal. Other than voltage equals energy per charge, that's true. But in terms of the electric field that we're creating here, okay, what's the equation up there that we're going to find helpful in determining the voltage of this thing? Think about like what we did over here to determine the voltage of a thundercloud. Think about it like this. Here's our thundercloud. Here's our curves, right? Like the ideas in physics is, oh, we can apply this idea. It's the same physics going on here. The same physics of me throwing a ball on Earth is me throwing a rocket to Mars, really. Okay, when we work out those ideas, we can apply them. We launch rockets, we can do these things. We launch now. Mars will be up. We'll get it. So, what do we need to know? What do we need to measure? We do have to measure this, yeah.
Can you measure the electric field?
How can we measure the electric field?
I don't know. That's what I was asking.
Oh, okay. So, if we knew the electric field and we knew the distance like we did here, then we could get the voltage. Okay, we're gonna add something else that's like because it's the same thing to say. So, anybody have any more thoughts? Kind of a little bit more to that. How are we gonna measure the electric field? Lights. Lights. One of these days. Somebody need lights. Lights. All the lights, please. It was a dark ever find more. What have we achieved here in this error?
Light.
There was some light. Does everybody remember the Does anybody remember what we call that? It's like a lightning strike, right? Remember the thundercloud in the ground? Yeah. Electrical breakdown. Does anybody know what the value is for electrical breakdown in air? That is the value. I was waiting for the units too. 40,000 is the value, but in what units? 40,000 volts per centimeter. So, what do we need to measure now? If we know the electric field that causes that, okay, then what we just observed, then we do know E, right? We don't have to measure, we can kind of use the literature, use the problem, we solved earlier. Yeah, that's not just a made up number, that really is the value of electrical breakdown in air. Now, it does depend on like how humid the air is and things like that, which is why I would say, okay, we're sort of using this known value. We'll measure the distance, okay? And note that as I bring this closer, sort of what happened. We saw maybe a stronger sort of discharge, right? And that's because what happens is you decrease the distance. What would happen to the electric field if you decrease the distance? It gets stronger, right? Because it's in the denominator. So distance in the denominator will be making that lower and lower, right? Bringing that closer together. Distance is decreasing. The electric field strength is getting stronger and stronger and stronger as I bring these closer together. Every time you type a key in a keyboard, it's like a parallel plate capacitor that you're discharging. Strike a key. That's a signal to the computer. That's the letter E. Right? So every different key is like a capacity discharge. And that's again emphasizes the idea of, hey, this is useful. This understanding of physics. We can invent technologies that do things like type, my lab reports and stuff. Okay. What do you think will happen if I have this thing is free to spin? Contrast. Yes.
Gonna like propel really fast.
Yeah, so the idea is like force on a charge, right? So in the electric fields exert forces on charges, just like in a gravity field where mass is a force on our mass, right? The weight that we feel. So if we hold this sort of here, it's kind of like the electrons deposit onto these points, and then there'd be a force on those charges. And so you kind of think about if we can get things to spin, okay, turbines to spin, that is at the heart of how we generate electricity. All right, and I mean, just think about it like this: human beings need ways to spin turbines, because if we can spin a turbine, we can put that turbine between like permanent magnets, and when you sort of cut across a magnetic field, you induce current. You can send them a power line. And some ways that we've thought of to spin turbines are like, let's put a water turbine somewhere where water can flow down. The water evaporates, it goes up high, and kind of harnessing that. That's hydroelectric power, right? So it's a water turbine. Most turbines are steam turbines, though. It's like we'll use water, but we'll turn it to steam. How can we get water to become steam? And some ideas are, let's mine fossil fuels out of the ground and burn them and heat up the water with that, right? So oil power plants, coal power plants. It's just about heating up water to steam. That's all it's about. Are there other ways to turn water into steam? Some people say, well, let's mine radioactive material out of the ground, enrich it, and start nuclear reactions to heat up water. That will work. Okay, so nuclear power plants exist, but it's just about turning water into steam. Down in Martin County, just south of here, they have a power plant that is around the one with cylindric. So it's like these parabolic mirrors that on the focal point there's like a like a container where they can put water or some kind of a fluid, so that as the sunlight hits this, it reflects, every reflected ray goes to the focal point, heats up that water and turns it into steam. So you have sunlight. That's quite smart, right? Especially in the sunshine state. But it's not always sunny, and so you need like a backup plan, so they can actually turn it to, I think it's a natural gas power plant. So it's kind of burn natural gas to turn the water to steam. But if you think about well, when it is sunny, why don't we have power plants that like do that? Just reflect sunlight to like a big tank of water, turn it to steam. To me, that seems more reasonable than mining radioactive material out of the ground. But there's arguments to be made about having a diverse sort of energy portfolio. If you want to have a lot of different ways to generate energy, but distributed generation. If we can let every house be like a little power plant, solar panels. So it's not just one power plant powering down to the people, but power from the people. Everybody that's sort of their own full power plant. Be more mindful about how much energy you consume, because you're also producing. You'll be like, I don't want to consume more than I generate. I don't want to be like a net sort of zero. And there are zero energy homes that produce just as much energy as they produce. So getting things to spin, like we can harness an electric field, right? So like harnessing lightning, that's tough because it's hard to predict or strike. But places where there's lightning storms or lightning is bound to hit eventually, is there a way to sort of harness that energy? Remains. All right, so I'm probably shocking myself doing this stuff. You kind of see, I'm like to shut up. So, this is an insulator, I'm getting clear. This is a conductor, so it's going to discharge pathways. There's a lead charges from the ground, it discharges into one. Rather than, it's like, let me investigate this and put my head really close, like to discharge into my brain, I'd rather have it, discharge into this. Some of y'all take psychology, if you here on campus. You learn about whose experiment was it for Milgram shocking people. And one of the guys, that was a test subject there, like worked with electricity. He was familiar with it. He's like, I know what it's like to get shocked. I won't, like, he was one of the few that actually wouldn't continue the experiment. Remember, this experiment was like, kind of like, well, people just blindly follow orders with authority figures. And it's like, oh, let's not continue, right? So, for those of you not familiar with the experiment, it's like, they brought the, let's say the mark, the person that, wasn't involved in the experiment, like the test subject. They brought them in and said, hey, we're going to see if, like, we can convince somebody to get the right answers on the test by, so negative reinforcement. If you get the wrong answer, we're just going to administer a mild electric shock to you. Maybe that'll convince you to not get the wrong answer, right? Even though you don't. But if I get shocked, I won't want to be shocked so much, and the brain will come up with the right answer. So they have these people come in and they start asking questions. The other side is after who's feigning sort of injury, but every time it's like the answer is wrong, they get a shock, and the shock gets worse and worse. And then the people that are doing the experiment, like, looking at the scientists, like, this person I think is getting hurt here. Like, oh no, that's fine. We continue the experiment. That'll have to on depth report to listen to me, right? And it'll be very few people will sort of go against that. Well, I don't want to ruin their experiment. I mean, so it's like it'll just kind of go all the way to like kill the person on their side. I think that type of experiment now, I don't know if you get approval, human subjects is kind of like traumatic to the person. But anyway, one of those, and I think it was 73% or something like that, of the people actually carried the experiment all the way out to like where they, ended up killing, the person on their side, so really weird or whatever it was. But one of the, 27% minority was the guy that worked with electricity. He was like, I don't like to get shocked. And what's even worse than being shocked is like the anticipation of it. Like, you're about to get shocked. You're like, oh, so every time that I do this, it's like every time I go to turn this off, I was very nervous. Somebody. Like the anticipation of the almost worse. Where's the all right. I'm done this year. So I've got some 3-hole punches. We'll place them thusly. What do you think will happen? One of the learning objectives is to be able to sort of describe an electric field or draw electric field lines, right? You represent electric fields with lines, like you may have noticed on the chalkboard there. There's 1, 2, like 4 vertical lines. See the arrows pointing up. Why? Because the negative charges in the cloud and the positive charges on the ground give us the direction of like where would a proton go. The proton will be repelled by the positive charges on the ground. So I'm actually drawing the electric field, on the chalkboard up there. What's the value of it? 40,000 volts per centimeter. Why? Because it's the electric strike, sort of long. And so the evidence of the discharge is that, there's electrical breakdown. So what does the electric field look like? It's invisible, we can't see it. How can we maybe visualize it? So these particles here are going to have the same thing happen that's happening on the sphere. The electrons will be deposited onto them. They will repel each other, and then they will be charged, and they'll be like charges that will force exerted on them, and they will follow the electric field line. Now gravity is also going to affect them, because once they sort of fly off of the surface here, they no longer have the normal force, right? With the fact that there's gravity. And so you'll see evidence of an electric force, in the opposite direction of gravity, and some gravity sort of at work there. And you sort of be able to sort of visualize what the field lines look like for a moment by spying the 3-hole punches here. Everybody get the cameras ready. YouTube. I should have given that. I have to punch some more papers before second period. Slow here. Okay. That's slow motion capability of the camera. That's what you want. Have it split, right? All right. Slow motion capability enabled. Engage. as I stand here on planet Earth, grounded, the Earth is like an infinite reservoir for electrons. So the charges go into my body and into the Earth. No worries. Because then it's like, okay, starting on here, what if there's like a field that's like, shocks me? We want that, right? So we want that. So the ground, right? We're grounded. What's that? Grounded. What's a good insulator? Air. I'll put some air between me. My head's like right below Sagittarius A spot. Where are we? All right. So now there's air between me and the ground. That's a good insulator, and I'm no longer grounded. Like an amateur, my toe, I've got size 14 shoes, you guys, and so my toe is over the edge right here. What happened? It dumped it into this metal thing and went to the ground. So I gotta shuffle myself. The idea is that I want to become electrified, okay? And all the charges stay on my body, and then my hair will sort of go this long hair here. I'm gonna try that again. Keeping my feet centered on the plastic chair, not hanging over the metal, legs there. There we go. Spirit of life, love contact, I would give you a high five. If you gave me a high five, what happened? Just start and you into the ground first. And exploding later. Okay, so your previous is like anybody that wants to, the human chain to electrify everybody. Yes.
I like volunteer to do it, because like I'd be like sitting down if I had my food. Would you like use hand sanitizer before and afterwards?
Yeah, let's say we have some kind of safety first in mind. We go back to day one here. We can't continue to do science if we're not safe, because it's all past people we're out of school. So hand sanitizer, I suppose, at your own accord. We don't have time. All right, hold on a second. Let me center my feet here as best I can with the chairs. And give me a chance to get sufficiently electrified with it. All right, I'm fine. Yeah, I think that was just a hard high five. I just kind of want to do like an ET kind of like this. It's like it's part like we get it sort of jump between fingers like that. Hey, yeah, we can try that, but let's like cut the lights off to do it, and we like actually see the spark jump. So like this, okay? This shit. Good. Where's my wooden chair? Oh no, I have one. however, we do need lights. So somebody volunteered with the lights here. We want to try to see if we can get a spark to discharge. All right, so we'll stand on here. Great. Okay, so there you go. That was non-contact. I don't even think we need to touch, right? So it's safe. So no hand sanitizer necessary, right? That's the way to do it. Anybody else want to share in that experience? If I see you later in the lunch line and you're like, you know, some of this a little mild aftershock from physics lab this morning. All right, so my footing here. All right, so our next volunteer. If you read my caption on Instagram, it's like, you may find the answer to today's essential question shocking. That's about 20 to get to the physics class, sorry. Well, we do need to answer the question, right? So what we should do is measure this distance. Like, let's not forget to do that before we leave. I'm coming out. We got Friday, too, so keep that in mind. All right, so let's go ahead and shock everybody that wants to get shocked here. Come on. You don't have to. Today's not scientist day at my student school. And they're morning. This is not scientist day. Okay. Anybody else to be shocked here? Let's take the measurements that we need. So you may have noticed that the discharge occurred even at this distance here. If you let it sort of run long enough, it will start to conduct across this distance. So really, you just sort of measure from like this surface to that surface, this surface to that surface, and that would be the distance d where we can see evidence of electrical breakdown. Maybe we should sort of move this to where like we can really see a good, okay, yeah, that's a good light start kind of thing. And then we'll get that distance, and then we'll use the electrical breakdown 40,000 volts per centimeter. We'll calculate the voltage on our bandwidth. Okay, so let's make sure that we actually do the answer the question. What time do we get out of here?
Like, we're like thinking that was hard.
We still got about 30 minutes left, so plenty of time, guys. All right. If we see here, that's like aftershock. All right. And so it's definitely conducting here. We hear a little, thunder, but right about here, all right. And so what we have to do is collect the data kind of like this. Oh, that's not good. All right. It's like we're measuring this thing. So it's like, again, safety first. Like, what would be a way that if you had to do this in the lab, you'd say, oh, I'd set it up like this. That would be an easy way to measure it. So like if I, sort of put the ruler like this behind it, where I could look sort of a level eyesight with it, and I sort of held this ruler up right here, far enough away that there's no chance that we would conduct sort of the rule. I mean, if it did, it wouldn't be that big of a deal, but it's like you kind of want the conduction to occur here, so there's where the electrical breakdown is. So, I can do my best to just kind of like hold it up like this, or if I really wanted to, I can get like a clamp, and a ring stand, kind of hold the ruler like this, horizontally across. That would be another way to sort of go about flipping. For our purposes, I'm just going to kind of go like this here. 10.8 centimeters, but then you can see it's like something was happening, it got weaker, right? Like it wasn't discharging much anymore. That's not a good sign. So you don't want to run this thing for like more than 30 seconds. Even over 30 seconds. All right, so 3.8 centimeters is the value that we want to use for that. So if we calculate all right, so we've said that the electric field that causes electrical breakdown is 40,000 volts per centimeter. I still wanted to make sure that the physics of gravity that worked. Sorry, for that. You almost made the price of the demonstration. So remember that mass in a gravity field, okay, very similar to charges in an electric field. I want to remind you all that the way that would be meaningful. You remember it. Good. All right. So this is mass, right? This is gravity. So gravity's still at work here. Don't forget about that physics. Okay, like I did. 40,000 volts per centimeter, and then we collected some data. D, 3.8 centimeters, and therefore V, the voltage, equals E D. And see how the units are already agreeing. So it's like if you know it in volts per centimeter, when we measure in centimeters, okay, if you want the added practice of, like, remember we converted this into volts per meter because we were given the distance 100 meters for that problem. You could convert it back into that, convert that into meters, just they have to be the same, okay? So 40,000 volts per centimeter times 3.8 centimeters is how many volts? What's a couple of 100,000 volts between friends? All right, 40,000 volts per centimeter. All right, 152 kilovolts. Okay. And that would be our answer to today's. Now, what about way out here where we saw it definitely was, and here I can have a better sort of measure because I'm not, so it's like almost exactly what that is. Actually 10.3. So 10.3 centimeters, what would that be? The same electric field, and again, this is like in dry air, so how moist is the air? Like that. 40,000 times 0.103. I'm sorry, we kept it in centimeters, so 10.3. So like 40,000 volts per centimeter times 10.8. So what is it? 10.3. 10.3, so 412 kilovolts. So maybe something like that, a range like that, that seems high. Not as high as the thundercloud though. All right, so megavolts or something like that. So, and again, you see like we hear like a boom, like a thunder, like we heard the discharge, right? And it is the sort of the same phenomenon that when lightning strike, where it heats up the air around it, and that air sort of passes into other air and makes it sound like so hearing the lightning, thunder. There, not lightning strike. Okay. Answer the essential question, electric fields, did that one. So, the quiz. Maybe we could do it together before the weekend. That way we don't have to worry about the quiz. We'll just say, hey, yeah, we got enough time left in class. We used our time wisely. Let's do it. I will post the quiz, the focus, but I'll also cue it up here on the projector, and I'll put it on focus for the e-learning students so they don't have a hard copy of it. Although I can maybe share my screen and do an electronic copy of it.